The second issue that we had is we had access only to one of the terminals of load and source. Okay, so access to only one terminal of RL and VS, right? So how do we tackle it? So first of all, let us put down what we have derived so far. So we said that we have a 12 volt supply. Okay, we have only one supply, and from there we'll now I'm not going to connect RD here. Previously I connected, now I will not connect because I am going to address this problem, right? RL two terminals I don't have for access, so only one side. Let me remove the RL from there because I cannot put it there. I don't have access for two terminals. Similarly, I will not put VS also. Okay, and then here I have two resistors which acts as voltage divider, so that this particular voltage is 3 volt. So this should be 9 mega and this should be 3 mega. That's what we derived. And yeah, so this is a perfectly valid circuit where drain voltage is 12 volt and then gate voltage is 3 volt. Okay, now the point is I have my source voltage with the source series resistance. I have my load, okay, whose one terminal is not accessible for me. Okay, so now how do I connect them? That is the question. Okay, because this has to be connected to the circuit. So incremental equivalent for the transistor, let me draw again, because we said that we established the fact that we wanted an incremental equivalent where load should be connected like this and then the source should be connected like this, Vs Rs. Okay, and this is a gate, source, drain. Okay, so now I need to connect this drain, this particular terminal of RL to the drain and this particular terminal of Vs to the gate, okay, or Rs to the gate. This is something that I need to do for achieving the incremental equivalent that I wanted. But what happens if suppose say I connect them like this? Okay, and also here also I connect them like this. Okay, so what is the problem? The problem is that I had designed my voltages and my entire DC bias point in such a way that I want a drain current ID to be 1 milliamps. Okay, similarly for achieving 1 milliamp, this voltage is designed to be 3 volt. Okay, that is how these resistors are chosen. Okay, now if I go and connect a source, okay, if I connect a source to this particular point, then certainly there will be some current flowing in this direction. Okay, because we said that all the current is flowing, voltage divider whatever we had set up was valid only when all the current is flowing through this 9, all the current that flows through 9 also flows through 3 mega ohm, right? And gate doesn't draw any current, so it was perfectly valid. Now the moment you connect something here, there will be some current flow in this direction, right? And which is something which will create problems because this voltage will no more remain at 3 volt, right? And similarly, the moment you connect some node here to RL, this current will no more be 1 milliamp because part of the current will also flow through RL, DC current, okay, which is something we don't want. We want only AC current to flow through RL, and we want only AC voltage of Vs to affect the gate node. Okay, in the incremental picture, the Vs voltage should not affect this particular gate node in the DC picture, and similarly this RL should not affect this particular drain node in the DC picture. So how do we do it? And of course the problem is that you don't want any current to flow in this direction. Similarly, you don't want any current to flow in this direction. Okay, and it should be perfectly valid for any kind of source you connect and any kind of load you connect. So it's not like you design in such a way that for this particular load, this transistor and this gain constraint, everything will be satisfied. No, it is not what I wanted. Irrespective of the source I am talking about and irrespective of the load I am talking about, there should not be any current flowing in this direction and this direction. Okay, DC current. Okay, so how do I achieve it? And we know capacitor is one element that will block DC in steady state. Okay, so if you put a capacitor here, and if the capacitance is sufficiently large, let us call it an infinite capacitor for now, and let us define what is actually large later. Okay, so if the capacitance is sufficiently large, in other words, if it is called an infinite capacitor, then it may act as a voltage source. Okay, so what I am saying is, if it is 3 volt, this capacitance, which is very large, will also be equally charged to 3 volt, so that if this also has 3 volts across it, and this node is also 3 volt, then 3 minus 3 0, so no current will flow here, right? Because you have 2 nodes at same potential. Between those 2 nodes you will not have any current flow. Similarly, you put another coupling capacitor at the output, which is sufficiently large. This will be exactly same as that of the node voltage at the drain. Okay, and it will automatically block any DC current that is flowing in, in this direction in steady state. Okay, this is the simple logic that we have, and these capacitors are often called as coupling capacitors. And the use of coupling capacitors is to avoid any kind of DC currents flowing to the source or to the load. Okay, so that your DC operating point is not disturbed even in the presence of source and loads. Okay, so now you make the full connection. So we will be using these coupling capacitors for all kinds of amplifier circuits to couple the source to the input node and load to the output node. Okay, and this is a very important concept, and I hope it's it's very simple also. So I hope it is very clear to you all. Okay, so by now you should be very much aware of each and every element in this particular circuit configuration. We are actually progressing towards the final amplifier, but then I hope everything as of now is very clear to you. So now see if it is complete. Okay, just check if it is complete. What do I mean by that is, you check if this results in the incremental picture of what you wanted. Okay, if this one or not. So first of all, source is connected to this particular node, source is connected to the gate node, and of course if the capacitor is infinitely large, it can be assumed to be short. Okay, because as long as the capacitor is very very large in AC domain, it can be short. So in signal picture it can be assumed to be short, but then I will tell you what should be the actual value of the capacitor should be to be assumed it to be short in the later part of the lecture. And then the gate terminal, at the gate terminal you have 2 resistors. One resistor is 3 mega ohm connected to ground, so it's 3 mega ohm, or R1 rather, this is let's say R1 and R2, so it is R2. And then another one is like 9 mega ohm, which is R1 connected from this point to 12 volt, and 12 volt is DC, so that is also grounded in incremental picture. So you have another resistor 9 mega ohm that is also grounded, okay, from this point to this point, so it is parallel combination. Okay, and then you have GM VGS. VGS is this node voltage. Okay, and at the output what will happen, so you are done with this side. Okay, and capacitor, it is short, so you have capacitor short and RL, and from this node you have a short to 12 volt. From drain terminal you have a short to 12 volt, and 12 volt is incrementally grounded, meaning you have a short here, right? As far as this picture is concerned, you have a short here. If you have a short and you connect anything across it, it is as good as not connecting it. So it's like this node is not there at all, and what is you have a current that you are wasting, it's going to ground. Okay, this is actually shorted, so there will be no voltage in this particular across. Drain is connected to source is grounded, so there will be no drain voltage or there will be no output voltage in the signal picture, which is something you do not desire at all. You don't want it, you want some output voltage. So what should happen? You should connect some kind of a bias resistor, okay, and call it RD, okay, just to avoid this potential going to ground in the incremental picture. Okay, so if I connect like this, then I will have RD here and this RL will be intact there. Okay, this RL will be exactly there where it was if you put RD here. Now, but the problem is that you have RD and RL in parallel and the gain will be reduced. Okay, but you have to live with it. There is no other option you have, right? So this complete picture, okay, is the common source amplifier. It is often called as the common source amplifier. Okay, so why it is called common source? As I said, you see the incremental picture. Okay, in the incremental picture, whichever terminal is grounded is common to input as well as the output. Okay, so you call that as that common, because your source is common to input gate and output drain, you call that as common source amplifier. Okay. So what will happen? Let me redraw. It is cumbersome here, so let me redraw the incremental picture. So it's a practice for you. You can also do it. So the thing is, first let me draw the source part. So I have my Vs and Rs, and then I have my gate terminal at which I have R1 parallel R2. Okay, this is R1 and R2. I am not showing 9 and 3 anymore because I want to derive the gain in a generalized fashion. Okay, so R1 parallel R2 is there. R1 parallel R2. Okay, and let me put a capacitor for now, C1, and assume it is infinite. Okay, but still let me not assume it is infinite. Let me not say it is short. Okay, I will derive the condition for which it should be short. Okay, and then this voltage is VGS, and on the other side, output side, you have GM times VGS, and you have RD, and you have a capacitor and RL. This is C2. Okay, let us call it C2, let us call it C1. I derived this circuit from this DC picture. Okay, so first things first, before going into any analysis, let me say, if you are given a circuit like this, if suppose you are given a circuit like this, so you most often you would not say, for example, I have given you this circuit and these are the parameter values, and then I am asking you to evaluate VGS, VDS, ID and all these things. How would you do it? Okay, so the first step is that you open all caps and short all inductors. If there are inductors, you short them. If there are capacitors, you open them. For example, I have two capacitors. If I open them, this part of the circuit and this RL part of the circuit will not at all be there in the picture. Okay, so essentially it is done to nullify the signal sources and the load. Okay, so even if you don't have capacitors and then signal sources are connected directly, you nullify them, meaning if there are voltage signal sources, you short them. Okay, and this is the main constraint that you have to do. And then second thing is, you find all the DC operating points or the quiescent points, you estimate them, and to estimate them you have to use the IV relationship of MOSFET, whatever we had done and all these things. Okay, so that will come with practice, and if you solve assignment problems, it should be easy for you. Okay, then deriving the small signal equivalent from the DC picture. For that, this is for DC analysis. Then second thing is for incremental analysis. So what you should do is, all DC voltage and DC currents you should deactivate, meaning all DC voltage should be shorted, all DC current should be open. Okay, and every non-linear element you replace them with their incremental equivalent. Okay, and if there are linear elements, they appear as it is, linear elements. Okay, they appear as it is. Okay, so you see, that is what I have actually done to derive it. For example, signal source will appear like that. Okay, and capacity DC voltage source only, it's deactivated. Signal source will appear just like that. Okay, if you want, you can add that as one more point. And then capacitors, it's a linear element that will appear as it is. Capacitor that is initially sharp to 0 is anyway linear, so that will appear as it is, and resistors are linear, that will appear as it is. This 12 volt voltage source is non-linear essentially, and that will be grounded because incrementally DC voltage is a ground. And then you have transistors incremental equivalent, because this is a non-linear element, I replace it with its own incremental equivalent. This is the whole part of the transistors incremental equivalent. Okay, and then you have RD appearing as it is because it is linear, and C is linear, RL is linear. Okay, so done. That is how it is being derived. Okay, now what should we do? We have this, we have to estimate the gain. Okay, before that, the first step is to figure out what should be the value of the capacitor for it to be treated as a short circuit. Okay, so you proceed in this fashion. Essentially you treat them as first order, okay, because they are disconnected. Anyway, there is no connection there. It's of course this is grounded, it's not that there is no mere connection, but then this part of the circuit is disconnected from this part, so you treat them as individual first order circuits. Okay, and then you treat one capacitor at a time. While treating first capacitor, you assume the second capacitor is short. So capacitor constraints, okay, constraints, and treat one cap at a time. Okay, so how do we do it? So for the first case, say I want to treat C1. If C1 should be short, okay, what basically I mean by that is, if I have two resistances, say let me draw it here. Okay, if I have two resistances like this, if I want this resistance to be treated as short, then I want this to be as large as possible, okay, compared to this one. So if it is R1 and R2, so if R1 is much smaller than R2, then R1 can be treated as short, meaning when I add R1 and R2, because they are in series, I am going to add R1 and R2. If R2 is very large, then adding R1 will not matter at all, so I can treat it as 0. That is what I mean. Okay, so similarly, if it is a capacitor, then if I want to compare my capacitance to the resistance, then I should consider the impedance of the capacitor, right? So I want to have a condition where impedance of my capacitor, which is 1 by omega C1, j omega C1 essentially, but then 1 by omega C1 is the impedance of my capacitor, that should be much smaller than the resistor occurring across the capacitor. Okay, and how do I find the resistance occurring across the capacitor? If you have any voltage source, you short them, because we are just bothered about the time constant, capacitor, and what is the resistor occurring across it. So as far as C1 is concerned, C1 is here, and then I have input impedance. I have to figure out what is the input impedance. To the right of the capacitor, what is the effective impedance, which is nothing but my R1 parallel R2. And to the left of the capacitor, when this voltage source is shorted, I have only RS. Okay, and this capacitor C1, impedance of it should be much smaller than the addition of these two resistances. Okay, just going by the same logic what we discussed here. Okay, so it should be less than RS plus R1 parallel R2. This is the constraint. So at any given frequency, okay, so what will be my capacitor value? 1 by C1 should be, or rather C1 should be much larger than, that's why we said capacitor is large capacitor or infinite capacitor, but it's not like infinite value. If I want to find my C1 constraint, my C1 should be much larger than 1 by omega times RS plus R1 parallel R2. Okay, if C1 is larger than this particular value, and first of all I should know my operating frequency, and when I know my operating frequency, I can determine my C1 if R1 and R1, R2 and RS are known. Okay, so for at any frequency, if I choose my C1 to be larger than this value, then it will act as an infinite capacitor or short circuit. Okay, short circuit in the incremental picture. Otherwise it will not be a short. If it is not a short, what is the problem? Certainly it will also drop some voltage. It will not, if a capacitor, if it is not a short, then it will start blocking this voltage. Okay, so next thing is that the constraint on the capacitor C2. Okay, and how do I find the constraint on the capacitor C2? So let me put the capacitor C2, and to the right of the capacitor I have only RL, and to the left of the capacitor I should figure out what is the effective impedance. Okay, and you short the signal source. If you short the signal source, this VGS is 0. If VGS is 0, this particular current is 0, so it is open, so I have only RD. Okay, RD. So here 1 by omega C1 should be much smaller than, it's basically the impedance of this capacitor should be much smaller than RD plus RL, which implies, sorry, this is C2. C2 should be larger than 1 by omega RD plus RL. And when I say much larger, the usual convention is to choose them at least 10 times larger than the value. Okay, if this is, if you calculate this value, you choose C1 in such a way that it is at least 10 times larger than this value. Okay, that is what it is. And first step we have done, we have found out the capacitance constraints, and let me redraw the picture again here. So the moment you found the capacitance constraint, you can treat as though you have chosen the capacitor of those values, and the capacitor will be short in the incremental picture. So let me redraw the incremental picture, and the capacitor is considered to be short, and it's just R1 parallel R2. Okay, and then you have VGS at the gate node, and then you have GM VGS here, and you have RD, and you have RL at the drain node, and this is source, it's grounded. Okay, so now you have to figure out what is the gain. Okay, and for the reference, we started by saying gain is equal to minus GMRL for the inverter. That is what, for the amplifier, right? That is what we started with. Okay, we said that if you build an amplifier with basic constraints, like not considering the fact that I don't have two voltage sources and all these things. If I use two voltage sources, if I put in the signal source wherever I want and resistance load wherever I want, then I could actually get minus GMRL as my gain. But then we'll see, after building the common source amplifier like this, okay, we'll see what exactly is the gain that we will get. Okay, so this is the reference, but for this circuit, first let me figure out my output voltage V0. Okay, V0 is equal to this current, my negative of this current multiplied by the parallel resistors, right? So GM VGS into RD parallel RL, right? If VGS is equal to VS itself, which is VS, then my gain would be minus GM RD parallel RL. Okay, but VGS is not VS. VGS is equal to VS times R1 parallel R2 divided by RS plus R1 parallel R2. Okay, so what would be my gain, which is V0 by Vs, is equal to, I just substitute it here, I would get minus GM into R1 parallel R2 into RD parallel RL divided by RS plus R1 parallel R2. Okay, by the way, I assume that this double line symbol is parallel combination. Okay, which is essentially R1 parallel R2 is nothing but R1 R2 by R1 plus R2. Okay, so yeah, so this is what you would get. So now you see, I actually had a reference of minus GMRL, but what I have is far different from minus GMRL. But then under some intelligent approximations or some kind of careful choosing of the resistance values, you could still achieve minus GMRL or are very close to that. Okay, so first thing is, if I choose R1 parallel R2 much larger than RS, what happens? This RS when added to R1 parallel R2 should be infinitesimally small. Okay, it should be negligible. In that case, I could actually cancel out this R1 parallel R2 and this total denominator, because RS is nothing compared to this value. In that case, my V0 by Vs would be minus Gm Rd parallel RL, right? So which is nothing but minus Gm into Rd times RL divided by Rd plus RL, right? So here also, if I choose, if Rd is much larger than RL, then my V0 by Vs would be approximately equal to minus Gm RL. Okay, but the problem is, if I choose Rd much larger than RL, what happens? First of all, what is the Rd that I can choose here? In order to have 1 milliamps, I should choose only 10 kilo ohm, because earlier I had RL here, and if RL was 10 kilo ohm, I got 1 milliamps. Now Rd also should be 10 kilo ohm. So in that case, Rd and RL are same, then the gain would be minus Gm RL by 2. Okay, right? The gain would be minus Gm RL by 2 if Rd equal to RL, right? But then I am saying, if I choose Rd much larger, okay, then I can achieve the gain of minus Gm RL, which is true. But the problem is, for a fixed VDD, if I choose Rd very large, this node potential going to be very small. Okay, this, as I increase this voltage, this resistance, the drop here will increase, so the potential here will reduce, and this transistor would eventually run into triode or linear region. Okay, the linear region is also called as triode region. Okay, but so the transistor would eventually run into triode region, but this particular combination is saturation. But we have designed, or we have designed the amplifier for it to operate in the saturation region, then only you can get the maximum gain that we have discussed. Okay, so either you should keep increasing the supply voltage as you increase Rd, or your increase of Rd is limited. Okay, this is one problem you have here. So you have to carefully choose Rd and RL in such a way that you are trading off to achieve the maximum gain that you can achieve. Okay, so this is about the amplifier. So you can have a gain of minus Gm Rd parallel RL, and the gain would be minus Gm RL by 2 if Rd equal to RL. And if you can choose Rd much greater than RL within the allowable range of the supply voltage, then you are free to use you are free to achieve a gain of minus Gm RL. Okay, so minus Gm RL is something you keep in mind, which is the gain of common source amplifier, and this is the incremental picture of common source amplifier. Okay, so that's this winds up our discussion on common source amplifier.